Hey, we're working through the 2017 free response questions as we inch closer to the AP Calculus exam. And all right, question number 2 today is a polar function question. So this is going to be a BC only topic. And polar functions can be very overwhelming and intimidating. I think to truly understand the essence of polar functions, we have to commit a lot of time to them. And unfortunately, it's one of the last topics of the year, and we end up rushing through it a lot of times. But to do it right, we really got to slow cook it as opposed to microwave it. But I think by the time we get done with this video, you're going to feel really good about these functions. I think we've got a really crystal clear process that we're going to walk you through. So the first thing you'll notice is we do have two distinct polar functions. Now this f of theta function is going to be this inside one. Now you could put your calculator in polar mode and graph it just to verify which one's which and so forth. But hopefully maybe if this is something you can do without graphing. Now don't get me wrong, that first one f of theta, I can't graph that one without my calculator, but I can graph this other one g of theta. That 2 cosine of theta is a more common one. And so if I know for sure that pink one's G, then of course, then the other one's got to be F. And maybe that's something I don't have to spend my time on graphing. So I would strongly encourage you not to graph these on your calculator just because of the time commitment that it would take. And then we've got region R, and I'll try to shade that one in here. And when I shade polar functions, I kind of like to do it in a wiper blade type of motion. And then S is just going to be this region here. So if nothing else, we've got ourselves a colorful picture. All right. So the first thing that they want us to find is the area of section R. And just a real quick discussion on area in general. It's all about how we'd subdivide that region. And we call these sectors, okay? They look like triangles. They look like triangles, but technically they're sectors. And we're basically subdividing this polar region into an infinite number of really thin sectors. And I want to credit, I think this is a really nice image here. I wanted to credit calcworkshop.com, another great website with some really good information if you're looking for more help as you review for the exam. But this is why I like to think of all of my shading in terms of like a wiper blade motion that kind of works. Let's see if I can do this right. You're gonna rotate, counterclockwise. So if this is 0 radians and you're rotating, this would be pi over 2 radians, and you're kind of sweeping throughout the region in that way. But at the end of the day, what you really, really, really need to know is that the area of a polar curve is 1/2 the integral, we'll say, from alpha to beta, or you could say theta sub 1 to theta sub 2 of the R value or function squared. So in this case, when I think of region R, these yellow wiper blades the tips of those blades are bounded by function F. So that's the function I'm going to integrate so we're going to go integral 1/2 the integral from 0 to pi over 2. And we'll say F of theta. Boy, that still looks like a 0. I'm trying to say theta here. All right, squared. Don't forget your squared sign. And we're going to pump that bear into our calculator to get 0.648 as our answer. Now, the irony here is, even though it's a polar question, your calculator does not need to be in polar mode unless you are going to graph these functions, okay? So I very, very rarely switch my calculator to polar mode. I keep it in that function mode, and that's the easiest way to evaluate, an integral like this. The other benefit that, and it may not come into this problem, but kind of a little secret ninja tip here, is that when you go into polar mode, your calculator does not have the capability of finding intersection points anymore. And that's usually a task that you do have to perform on these questions. But if you keep it in function mode and graph these equations in terms of X, then you can find intersections and things like that. Okay, let's get into part B. And this is maybe my favorite part of this entire question. And basically they said, hey, there is some ray, theta equals K. Now remember, what does theta equals any number look like? Basically, theta equaling a constant is always going to create some kind of ray that goes right through the origin, okay? So this first one, this might be theta equals pi over 6. This might be theta equals pi over 4. This might be theta equals pi over 3, and so on. And they said there's one of these rays that divides region S into two regions of equal area. So we're going to write, but do not evaluate or do not solve an equation involving one or more integrals that gives the whose solution would give you the value of k. So let's go back up to our picture and see what this might look like. And let's switch to a red. We'll thicken that pen up a little bit. So I'm thinking if I put a ray right about here, and we could argue, whether you want to rotate that up or down a smidge. I think this region right here is going to be approximately equal to this region all the way around the horn until I get to here. And so basically, I'm going to set up two integrals. I'm going to do an integral that starts at 0 and integrates until I hit k. Okay, that's my first integral. And then my second integral is going to start at k and integrate until I hit pi over 2. So those are going to be the bounds you see on my two integrals. So let's see how this all sorts out. All right, we might have to drop that pen a little bit. Go back to black. Okay, so I'm going to say the first region is from 0 to k, and in the setup is going to be it's g of theta squared minus f of theta squared. Now, why is it g squared minus f squared? Well, remember, s is just that space in between the two curves. So in essence, I had to find all the area bounded inside of g first, and then subtract out all of the area bounded inside of f. Okay, we're going to close that bracket. Of course, that's with respect to theta. I'm going to set that integral equal to 1/2 the integral from k to pi over 2. And then again, the same setup, g of theta squared minus f of theta squared. And just a note on that setup there, it's very important that we're squaring just g by itself. And then again, we're squaring just the f by itself. If I was to do g minus f and then square it, that would not be correct. That would give me a totally different solution that's incorrect. So anyway, thank goodness we only had to do setup only, and just setting those two integrals equal to each other. If you were to solve that for k, you'd have the answer. All right, part C says, okay, let this new function named w of theta be the distance between the points with these polar coordinates. So let's see if we can draw a picture of what w might look like. So I guess in essence, w is going to be the distance between, let's see, any two points that fall on the same ray. So you could just pick any random ray that you want and take this point, and the distance between them, which would be this length right here, is going to be your w function. So I said w is simply g of theta minus f of theta. That's really all there is to it. So let's see if we can write that out. W of theta is g of theta minus f of theta. That's all there is to that. Okay, now they want me to find the average value of this function. So I'm going to say w, and then I like to use a little subscript average, so it's not confused with area, is going to be 1 over, and I'm thinking, can you picture that formula? 1 over b minus a times the integral from a to b of whatever function you're finding the average of. So this would be 1 over pi over 2 minus 0 times the integral from 0 to pi over 2, and of, we'll just write out g of theta minus f of theta with respect to theta. All right, now if I was cleaning this up by hand, and I don't know as this is necessary, that coefficient at the end of the day would be 2 over pi. And then you've got your integral, which again, I'm going to put into my calculator. And again, my calculator is not in polar mode. You don't need to be in polar mode to evaluate this integral. And I got about 0.485. And so the average distance between those two curves on any radial line is going to be 0.485. Now, I think we're going to use that number here in part D. Yeah, using the information from part C, find the value of theta for which w of theta. So I'm going to say, okay, w of theta was just g of theta minus f of theta. And I want to set that equal to the answer I just got, which was 0.485. So I think, again, this is now here in this case, this is a great time to be in that regular function mode on your calculator. So what I'm going to do is I'm going to graph this rascal as my y sub 1. And I'm going to graph this as my y sub 2. And all I'm looking for is the intersection between those two graphs. Okay, let's see where they intersect. Okay, my calculator says they're going to intersect when theta equals 0.517688 ... Now, it's very tempting to round that answer, but this is what we call an intermediate answer, not one of your final answers here. So it's very, very important that I contain or carry all those decimal values, and we'll just indicate that we're storing that somewhere in our calculator, perhaps alpha A. So now they want to say, is W increasing or decreasing a theta? Well, that's all going to depend on whether W prime of A is positive or negative. Okay, so if I was to derive W, I would just get G prime of theta minus F prime of theta. So this would be G prime of A minus F prime of A. And again, I feel like a broken record. We're going to evaluate that on our calculator as well. And let's see what we get when we do that. Okay, my calculator is giving me a negative answer. So I'm going to indicate that that's less than 0, which implies that W of theta is decreasing at theta equals 0.518, since we'll say W prime of that number is less than 0. So that's all it is. And I really, really hope you feel at least a tick more confident on these polar functions. It's just a totally different bear to try to wrap your head around. But with a little more practice and a little more practice and a little more practice, you're going to become really, really good at these before you know it. All right. Have a great night.